This is the highest bridge on the planet. Suspended 625 meters above China's Huajiang Canyon, it reaches the height of the nation's tallest skyscrapers. Crews battled unstable mountains and extreme winds to open it earlier this year. But this bridge wasn't built to set records, it was built to unlock an entire region. And it starts here, with connection. There's a reason locals in Guizhou say there's no 3 feet of level ground. More than 90% of this province, where Huajiang Canyon Bridge stands, is dominated by mountains and steep hills. The terrain is breathtaking. Often compared to Switzerland, Guizhou is internationally known for its landscapes, culture, and dramatic scenery. But that same geography fragments settlements, compresses farmland, and turns short distances into logistical problems that scale across the entire province, limiting how efficiently people, goods, and services can move. But beauty never meant accessibility. For decades, Guizhou functioned like an inland island. Reaching it was difficult, and moving through it was even harder. That isolation shaped daily life, trade, and opportunity. Entire communities developed around constraint rather than growth, with time, cost, and risk baked into every journey. It's why the Chinese state committed billions to physically integrate the region with the rest of the country. In the late 1990s, China opened Guiyang Longdongbao International Airport. High-speed rail followed, along with expressways crossing the province. Yet the core challenge remained unchanged. Mountains still dictated movement, transport corridors existed, but they bent around terrain instead of defeating it, adding distance and unpredictability. So the national infrastructure campaign pushed further, from surface access toward full topographic penetration. To make travel viable, Guizhou now contains roughly 32,000 bridges. Each one shortens distance across impossible terrain. They form a dense lattice of direct routes cutting through what once blocked movement entirely. This density isn't incidental. It reflects a systemic strategy to replace winding elevation with linear flow at a provincial scale. And the most consequential of them opened earlier this year. This is Huajiang Bridge. From the Beipan River below, its scale becomes unavoidable. The bridge spans the Huajiang Canyon hundreds of meters overhead. Before it existed, crossing this gap meant hours on narrow mountain roads. Today, the same journey takes just 2 minutes. That reduction doesn't just save time, it reshapes logistics, changes route planning, and alters how the region connects internally and outward. Time itself was compressed. That compression feeds directly into the Guizhou S57, a 150-kilometer highway driven straight through mountainous terrain. And not metaphorically. An entire mountain was split to allow the road through. Cutting directly through mountains is not a neutral act. Blasting rock at this scale reshapes ecosystems, alters water flows, and permanently scars terrain that once evolved over millions of years. From an environmental perspective, this kind of intervention is hard to justify. The landscape does not recover. The mountain does not grow back. But for China, the calculation was never ecological in isolation. It was systemic. Geography was treated as a constraint to be overridden, not preserved, in order to integrate an entire region into the national economy. Rock was drilled and blasted into a V-shaped corridor. The act isn't symbolic, it's functional, turning elevation into a pass-through rather than a barrier for regional traffic. This expressway links the Liuxi Special District with Anlong County. 14 interchanges distribute traffic across the region. What was once fragmented is now navigable. Movement becomes predictable. Distance becomes manageable. Local roads no longer carry national-scale demand, and long-haul transport no longer detours around geography. So yes, China cut a mountain in half, then connected it directly to the world's highest bridge. At this point, it almost feels expected. Even mapping how these systems interlock requires serious mental effort just to follow. The scale is such that individual structures only make sense when viewed as components of a wider national network. Huajiang Bridge is the final link joining highway segments on both canyon rims. Engineers surveyed 5 to 10 kilometers upstream and downstream to identify a viable crossing point. Soil stability, canyon depth, and span width all mattered. Each variable constrained the next, narrowing options quickly. Local geology ruled out simpler solutions before design even began. When combined, those constraints demanded something extreme. The chosen solution stretches 2,890 meters in total. Its central span alone measures 1,420 meters. In other words, connecting this region required a record-breaking structure. Not as a goal, but as a necessity. Anything shorter would fail the geometry of the canyon, and anything simpler would fail the demands of the network. Two design paths were evaluated: cable-stayed or suspension. Cable-stayed bridges rely on tall towers and direct cable support. For spans of this length, suspension performs better. Huajiang became a steel truss suspension bridge, a system proven in steep, rocky environments. Its efficiency lies in distributing load horizontally, reducing stress on individual vertical elements over long distances. Suspension cables anchor directly into solid rock. That anchorage delivers long-term stability. Before construction began, engineers ran virtual pre-assembly simulations. Every connection was rehearsed digitally. At this scale, sequencing errors cascade fast, so resolving them virtually prevents physical dead ends. Errors had nowhere to hide. The bridge deck is built from 93 steel truss sections. Together, they weigh 22,000 tons. For comparison, the Eiffel Tower weighs 7,300 tons. Huajiang carries triple that mass, all of it suspended over open air. Weight becomes both asset and threat, stabilizing the structure while amplifying consequences of error. And air is unforgiving. Dropping steel 625 meters would destroy it instantly. Accuracy isn't optional, it's survival. The world's largest crane, Big Carl, stands 250 meters tall. Even 3 of them stacked couldn't reach this canyon. Traditional lifting simply doesn't scale vertically here, so a different approach was required. Enter the cable crane system. Think of it as an aerial delivery network. Steel units move along overhead cables, not rails. Components travel from abutments to precise positions mid-span. The system turns empty space into working surface, allowing gravity to be managed rather than fought. It's engineering adapted to absence of ground. Construction begins at the center. The bridge grows outward symmetrically. Balance is maintained at every stage. No single tower absorbs uneven stress. The structure stays stable as it expands. This sequence isn't just procedural, it's structural insurance against imbalance. Placement precision comes from Beidou. China's satellite navigation system guides alignment. Each segment locks into place digitally and physically. But geometry alone isn't enough here. The ground itself complicates everything. Canyon walls slope unevenly. Foundations don't behave like flat plains. Just look at Hongqi Bridge in Sichuan, where nearby roads cracked under shifting slopes. In Guizhou, imbalance is constant. Load paths must adapt continuously to terrain response, not idealized models. That's why Huajiang's towers aren't equal. The north tower stands 262 meters tall. The south reaches 205 meters. Anchorage systems are asymmetrical by design. They respond directly to geology. Uniformity would introduce stress rather than remove it. Cables descend into the mountains at different depths. Some anchor deeper than others. Rock composition dictates everything. Symmetry would fail here, adaptation succeeds. Engineering becomes site-specific rather than formulaic. But static ground isn't the only concern. Guizhou experiences seismic activity. Not the world's most intense, but enough to matter. A long-span bridge behaves like a suspended pendulum. During earthquakes, motion is inevitable. Design must accommodate movement, not resist it. Rigidity would amplify damage rather than prevent it. Shock absorbers installed at each end help manage energy. They slow oscillations without locking the structure. At the same time, the bridge must expand and contract with temperature. Thermal movement is constant. Flexibility becomes protection. The structure survives by yielding in controlled ways. Then there's wind. Wind is among the hardest forces to control. At this height, wind is not a comfort issue. It is a connectivity risk. If the bridge closes, the region fractures again. Especially in a canyon of this depth. Canyon geometry amplifies airflow through the Venturi effect. Narrow passages accelerate wind speeds. Pressure drops, behavior destabilizes. What feels calm at ground level can become violent at deck height. The effect is common between skyscrapers. Here, it's magnified by topography. Wind funnels through tight canyon sections. Gusts reach speeds comparable to express trains. Stability depends on prediction. Because stability here isn't optional. This bridge carries regional traffic that no longer has a backup route. unknown airflow becomes unacceptable risk. Computer models help, but they aren't enough. Engineers built scaled physical models. Wind tunnels recreated canyon airflow. Structural responses were measured directly. This testing reveals interactions simulations often miss, but one more system pushed accuracy further. Doppler LiDAR mapped wind in 3 dimensions. Laser beams scatter through air and clouds. Reflections from moisture particles shift frequency. That shift reveals motion. Wind becomes visible. Because for this region, failure isn't theoretical. It would mean hours of detours, broken supply chains, and lost economic time across an entire corridor. Design parameters move from assumption to obligation. By layering geology, seismic risk, and wind behavior, design parameters were locked in. But completion doesn't end observation. Monitoring continues long after opening. Because this structure is no longer an experiment, it is part of a regional circulation system that must stay open every day. Huajiang Bridge cost up to $300 million. It was completed in just 3.5 years. Elsewhere, that would define a generation. In China, it defines a phase. This is standard output. Speed and scale operate together as policy. The country leads globally in high-speed rail length. It has more bridges than any nation. It has more dams. But Guizhou's transformation isn't about records, it's about redistribution. Infrastructure becomes a corrective tool. Since 2012, China has poured hundreds of billions into infrastructure across its poorest regions. This effort sits under the war on poverty. The goal is spatial integration, economic access beyond megacities. Growth is redirected rather than concentrated. Guizhou is also part of the Belt and Road Initiative, a network of economic corridors across continents. Each segment showcases development capacity. Huajiang isn't hidden. It's demonstrative, a signal of what internal capability looks like at scale. Huajiang was built with global attention in mind. China expects it to attract visitors. An 800-meter glass elevator lifts tourists into a 2-story cafe inside a support tower. Experience becomes infrastructure, function and spectacle merge deliberately. A glass walkway hangs beneath the roadway. Visitors look straight down into the canyon. An artificial waterfall spills across the span. Engineering becomes spectacle. Movement becomes destination. The bridge itself becomes an economic node. Beyond tourism, extreme sports factor in. A bungee platform launches jumpers from the highest bridge on Earth. Plans include professional base jumping events. Even a canyon-level sports center is discussed. Risk is packaged as attraction. Huajiang Bridge is an engineering achievement, but more importantly, it's a connector. It proves national systems can override geography. That mountains are no longer boundaries. They're obstacles already crossed. Connectivity becomes state infrastructure, not local exception. Hundreds of millions, sometimes billions, are invested to create these corridors. Routes don't just move people. They generate revenue, visibility, and cohesion. They reshape regions. Physical connection becomes economic leverage. Bridges like Huajiang aren't just crossed, they're visited. They anchor transformation in physical space, and they reveal what happens when a country cuts through mountains to connect itself. Thanks for watching. If you enjoyed this breakdown of China's mountain infrastructure, make sure to subscribe for more deep dives into the world's most ambitious engineering projects. We'll see you in the next one.